Well, good morning, and it's a pleasure to be back here in Baku. It's been about 2 years since I've been here, but it's actually also a pleasure to be back at an ENOG. I apologize for missing a few previous ones. They're always a fun event and meet interesting people. For those people that know me, I now work for CloudFlare, and started to focus a lot on content and CDNs, and also on protecting against DDoS attacks. And that's what I'm going to talk about today. But don't worry, I still care a lot about IPv6, and will continue my my push that I've had for years as to the importance of IPv6. What I'm going to talk about today is I'm going to break down some DDoS attacks and look at both ways of protecting it and also ways of stopping this in the first place. And because of that, I'm going to start with this very near obvious statement and then show the information behind it. DDoS attacks, the ability to take multiple players and attack against a single player on the internet, are becoming more prevalent, more intense. They're becoming more commonplace. And as I'll show, they're also becoming quite easy to initiate. And I'm going to take it from our point of view because, and I'll explain why, we end up being a fairly large entity that gets attack traffic, and we can break down and use that to our advantage here. But if we go look at some of the dates and times and amounts of attack traffic that we have seen, you'll see this obvious growth in the charts, of which we really don't know where this is going. It's going up, it's getting bigger, there's no doubt about it, but over time we're absolutely seeing more and more ability to generate traffic with more and more techniques. And I'll talk about some of these. But first, I'm just going to give you a background of where we are and why, and more importantly, why we are seeing this. We run a network in multiple locations around the world. We build in each of those locations in an identical manner, and each one is built as a protected place to run content delivery and also to do this DDoS mitigation both on DNS and on content. We have customers from around the world, and we do actually have customers from around here. We definitely have a lot of customers out of the ENOG region in general. But the customer base is split between, or the spread between very high-end customers and enormous amounts of small networks. In fact, probably about 1.5 million or growing individual domains that are connected to us for either content, well, for content delivery, but also for this protection. And this is very valuable, because this long tail of customers provides us with a massive honeypot of traffic. And you'll see a little bit of that in the background noise. Somebody somewhere is always seeing some form of attack traffic, and we can model that very successfully. So let's talk about, over time, what's happened. Let's go back a couple of years, look at the easy attacks, and we'll move forward and see what the technology and the response has been. We go back originally only about 1.5 years, and this was the Spam House attack. Turns out it's uninteresting who was attacked. Spam House itself is an entity that keeps track of IP addresses that are perceived to generate spam. And therefore it's a very useful filter set and the basis for a lot of spam processing on mail servers around the world. Some people don't agree with that list, and those people decided to take Spam House off the net. it's easy to see them off the net right there and then because their website responds with unable to connect, no content. Whichever browser you're on, a different error message, but that was the net result. That was what they were after. So it starts with a very simple attack. 10 to 80 gigabits worth of data is trivial. But not if you only have 10 or 20 gigabits worth of connectivity into your site where you're hosting your data. It's quite understandable to see 10 gigs worth of connectivity. This is a website that, for all intents and purposes, doesn't generate very much traffic. It doesn't need to. It isn't a massive news aggregator or a search engine or a big picture database or a video. So it's just a bunch of text. So it doesn't need much bandwidth. So by sending 10 to 80 gigs worth of traffic, you really don't generate that much of a problem. But of course, sending up to 80 will cause you a problem, especially when you look at the graphs and you suddenly see that this is the type of graph that goes instantly from regular traffic to on. Now this graph is actually taken at a more aggregation point, and it shows this, it shows that obviously other people are being attacked because this is many websites, many different suppliers, many different customers that are against this particular supplier. This isn't good. Obviously, Spamhaus moved their services over to us. That's sort of the key message here, where this type of bandwidth could be handled quite happily. But that wasn't the end of the conversation, because a day or so later, it got a little bit more intense. Then we started seeing 300 gig attacks. Now, I'm going to break down how the attacks were done, which is really the sort of the fun part of this, if you want to use the word fun. But the reality is that this is the type of traffic levels that you see on these attacks, and we'll repeat these as we see other attacks. The ability to go from nothing to this amount of bandwidth. And by the way, measuring this much bandwidth must mean that there's at least that much connectivity capable into this particular supplier. This is a really large amount of bandwidth. But let's continue and look at another attack. So earlier this year, in the beginning of the year, we saw a different style of attack. Now, this is sort of a more interesting graph. By this point in time, there were some interesting ways of graphing stuff. This shows an ability to see that the attack was generated all over the world. It wasn't a particularly individual source. It was from everywhere. There were a whole bunch of machines that were being summoned in order to do this attack. Again, we see this instant on, this instantaneous ability for traffic. We're looking sort of here from the left to the right as time goes by, and first thing in the morning, or early in the morning on Tuesday, depending upon your time zone, and whoomph, you're seeing a large amount of traffic. This was just a simple graph that ended up on Twitter from some other provider and said, wow, we're seeing this, and we're seeing all this traffic heading towards CloudFlare. We saw it as well, because obviously it was heading towards us. If you actually look at it over time, you'll realize that, this one's the biggie. This is the best we've seen so far. And the question is how and why and what was going on, what was different about this. But definitely compared to the noise over the last couple of years, this one got real as well. But let's break them down. Let's have a look at what they do, because if we understand how they happened, we also can understand how to protect against this. So basic DDoS mechanism. This is the simple chart of how a DDoS works. You simply take a regular viewer of a website and you replicate it with a set of attacks. Now it turns out, and this is the key part of this, you don't actually need to go look at a website in order to attack it. You just have to send traffic towards a website. because traffic will fill a pipe. When you fill up a pipe and a regular user can't get through, boom, you're done. The regular user can't get through, that was your ultimate goal, etc., etc. And that's what you try to protect against. The mechanism, if you break it down on an individual attacker, is pretty much as simple as it can be. But there's a reason why this simplicity works on the internet, which I will talk about in a second. But here we sit as the attacker with a very particular IP address, but we simply send out a request that says, can you respond to me? Oh, by the way, my IP address is something different. And what happens is you don't get the response, but the place you want to attack does. So what we have here is the simplistic numbers. We have an attacker sitting at a random IP address somewhere. He may not know that he's the attacker. This may be what's called a bot, an entity that has been used. But he's sending out a request with a different IP address, going to a server who then, instead of responding, goes off to where you want to attack in the first place. This is both very simple, but brings up this really fundamental question. How can you do this? How can I turn around to somebody and say, my IP address is something else than it is? And it turns out there's a lot of history about this. And it actually boils down to some very basic, simple things. Although this should be fixed, for other reasons, this is what makes the internet such an open and growing and capable platform. Not just this capability, but basically many, many capabilities. There's no control at the end point to the end point as to how and what gets talked about. You don't need permission from the inside. You don't need permission from the telecom or the ISP or the global network. If you come up with a new thing, this is attack traffic, so ignore that point for the moment, but this is really fundamental. The internet has grown to where it is today because you don't need permission to innovate and build new things. It so happens, unfortunately, you can use that for a negative thing as well. But why can I spoof my IP address? So let's now start. Now we're going to start on this journey as to why and we can do this and how do we fix it. So this is a graph that was taken earlier this year. I've got the URL is on the side, and by the way, I apologize. The presentation, the PDF, will be up on the ENOG website as soon as we copy it over right after I speak. And I apologize that it's not there before I spoke. So this website gets updated every now and again, and it's a measure of ISPs out there that allow this type of spoofing of IP addresses. They shouldn't. There is a set of documents that explain how to fix this, and we'll talk about that in a bit. But basically they took these are just different ways of measuring the same information, but basically 25% of all autonomous systems, all individual networks, in some way have a fully spoofable capability. You can tell that a lot don't. And you can tell that some of them are already working on this. These graphs, by the way, are getting better. The ability to spoof, which is a fundamental process used within DDoS attacks. This number should be 0%. It should be as close to 0 as makes sense. At the moment, it isn't. So let's continue. Let's break this down and actually look back at this 2013 attack. And this is how simple it is. Now it turns out, okay, I'm painting a picture as if you should go home and try this. Please do not go home and try this. However, this is what was done. It really only takes 30,000 machines that you can find out there and a laptop capable of generating 10 megabits worth of data to generate this massive multiplier up to, greater than 300 gig. This simple math obviously really needs to be averaged out, but the reality is that finding 30,000 machines back then was very, very simple. The attack simply is using a multiplier. I can send a small packet and I can find somebody out there who will generate a large packet in response. So in this case, we had what were called Open DNS resolvers. A DNS resolver is fundamental to the way the internet works. We all use them day in and day out. When we type in a URL and we want to convert that to something communicating on the internet, we're taking a human typed in name and replacing it with a set of numbers that then can be used as in the packets to move things around. And we're done. The name has been converted to a number and we're done. It turns out an Open DNS resolver will quite happily do that conversion for you independent of your IP address. And it actually turns out that Open DNS resolvers are not needed. An ISP or a major network in a corporation can have its own DNS resolvers that respond to its own network and no one else. An Open DNS resolver will respond to anybody in the internet. A packet could come from Australia and head towards Finland and then be responded. A bit inefficient, but if it is open, so be it. There's a lot of Open DNS resolvers in there, and we'll see the graph of how that fixes itself. But here we have this magic ability to send nothing more than 64 bytes, a tiny packet, and get a resolver to respond with a very, very large response. How large and how easy? Very easy. So here's the command used to generate a query. It's a very simple command. You can dump that into a Linux box or a Mac on a terminal. Of course, the part I'm not providing you here is the IP address of an open resolver. We're not going to let one of those IP addresses out in public. The response is this massive response of packets. This is an awful lot of data here. The reason being is because the query here is a really impractical query. This is something we don't need to do in real life, but it's left over. And you'll see that repeated a few times. So what is the query here? The query is for any information associated with this particular domain, and it doesn't really matter which domain I pick, but this is a nice, simple one. I have to find an open resolver to query. That, of course, is my first thing. And I have to do a bunch of other commands here, most importantly, to make sure I end up saying I want lots of data. And this query itself would actually respond back simply to the sender. There's no spoofing of IP addresses here. And why is this response so large? Well, look at this response here. What's happened is we're seeing all of the DNSSEC information. We're seeing keys that come back for DNSSEC. These are fundamentally larger than any other DNS request out there. And I'm not going to delve deeply into this, but the reality is that DNSSEC, because of its complexity, because of the extra data, this is stuff that the end user never sees. We now have a mechanism to generate large packets. So fixing the Open DNS resolvers is very important. Here's the simple math, just to reiterate it. One laptop, find a handful of servers that are compromised, managed to generate about 9 gigs of DNS requests, and all you have to touch is 1/10% of all the Open DNS resolvers that are out there. Now, this attack occurred, and it definitely generated a lot of data. But then it generated a lot of people saying, this is wrong, this should be fixed. And in fact, actually, the one great thing about this attack was it fixed an enormous amount of servers. And in fact, I have the stats later. This is I want to now talk about this one. So first off, Twitter is your friend. Twitter is the new way of debugging networks. For everybody that's a network engineer here who has all those nice fancy tools to monitor networks, turns out Twitter is your friend. Because somebody in the rest of the world will tweet, there's an issue, and you go, oh, it's not just me. These are some of the tweets that showed up within minutes or hours, actually hours of the attack. But I picked them for a particular reason, because they show 3 different things occurring. First of all, at some random network, actually not that random to be honest, but this is OVH, and this person's seeing a large attack. Well, we saw a large attack. Now we knew other people were seeing it as well. The middle one here is Brian Carpenter, who is a very respected researcher, who says, oh, I think I understand how this attack works. Here's the source code for creating it, written from scratch. It's that simple. And then finally, this is my boss, who actually, and we'll see this, we took a bunch of statistics. In this case, this tweet's about China Mobile, and we got them to get rid of an enormous amount of their vulnerable servers. In this case, we're talking NTP servers. So this diagram looks identical, except for we're not pinging, we're not doing a SYN attack, we're not doing DNS attacks, we're doing NTP attacks. But look at these numbers. This is the key point. 64-byte request is generating a 13,000-byte response. This is a much larger multiple, nearly 4 times as much traffic created for every query than the original DNS query. Now we don't even need as much to generate even more traffic. Again, this single laptop having this ability to generate this much of an attack, the simple math of what we have here. But why are we generating it? We're generating it because there's this one command left over in the NTP world from the debugs of years and years and years gone by, and no one deleted it. So these are the type of multipliers that we know we can see out there for these type of protocols. The NTP protocol multiplier we think is about 200 plus, but we know that vsNTP could generate an enormous amount higher than that. The good thing is that we don't see a way of finding those open vsNTP, so we don't think that future methodology is really doable, but look at some of these numbers we're seeing. So let's talk about how we protect it, and let's look at how this stuff is monitored. So first off, let's go back and look at the websites that monitor this and see how we fix things. Originally, we saw an enormous amount of open DNS resolvers. This DNS attack looked like a fairly spread out environment. Now, most of these open resolvers turned out not to have very much bandwidth behind them. So if you found one, you couldn't do very much with it. You could do some damage. You definitely would generate packets that you should not. But they weren't well connected, but some of them were very, very well connected. I recommend having a look at this particular URL for a very specific reason. Along here, you can type in your own IP address for your own network, for your own ISP, and you can see how well your network operates, and if you have boxes that you should fix. How easy is it to fix? It's so surprisingly easy. This is again taken from Team Qumra. You can find this with a simple search. How do I protect my NTP box? You'd find it pretty quickly. But what it says is that depending whether I've got a resolver or an authoritative server, here's I use the bind examples because they're fairly easy to read. But basically, you need to make sure that you've got recursion turned off and you don't send additional information. All these extra bits that are useful but aren't needed in this particular case. In this case, you've got a slightly more complicated environment if you're running as a resolver versus authoritative. But the point is that these are very simple. It should only take a few minutes to understand how to change your network to do this. The other attack that we talked about was the NTP attack. And again, if this web page looks very familiar, it is. It's sort of the same group that said after this attack, ooh, let's go out and measure, let's make sure. Type in your IP address, work out where, if you have anybody that is potentially open and that needs to get fixed. The NTP attack required this monolith command, this monitor command. And again, the same issue, we'll see how to fix that. But if you look at the graph, I only have it up until the end of, to this year. But I'm sorry, I only have it during the attack period. I don't have it beyond that. But this is a good example that we managed to get less and less traffic. As soon as the attack occurred, people realized that this was a problem. People react quite positively, in fact, actually, on attack traffic. This is surprising. People will be motivated to fix things. If we'd had this level of motivation in the IPv6 world, we would be a lot further along now. Again, Twitter is your friend. You'll find a lot of good experts out there talking about it. But the fix is very simple. This again, it actually comes from the same. It comes from the same website. But the reality is that you have the ability to fix this type of configuration very quickly, very easily, without too much difficulty. The command should never have been in there. It was used for debugging a long time ago, but the internet got a lot bigger, and that bigger became the fact that it became more of an issue. But now let's talk about the big issue. In reality, just about everything that I talk about is about the ability to spoof IP addresses. That's the core, the beginning of the process. And the beginning of the process is where we need to go fix the problem. There is this fundamental BCP 38, best common practices, which is required. It's absolutely required if you're running an access network, if you're running a broadband network of some variety, if you are operating anything that can create packets, which is just about everything on the internet. BCP 38 says very simply, if you own a set of IP addresses, an IP range, only allow packets out from that. Fixing BCP 38, fixing your network to be BCP 38 compliant, which is not hard in the big scheme of things, has the ability to fundamentally change the amount of attack traffic created out there. BCP 84 is a follow-on from that, which just simply has the ability to handle multi-homed capability, but it's really the same language. I'm going to talk to you a little bit about what we're doing because that's sort of like the follow-up, the final part of this, but I want to explain some of the mechanics that we've used. Those 1.5 million customers are very useful. They generate this constant attack traffic. We see lots of attacks, very minor attacks coming in. This is a simple sort of graph of what happens. We see attacks coming in. The first stage is a set of automated software that can do this. I don't really want to talk too much about us. I just wanted to say that it is possible for some of this attack traffic to do things automatically. We're around the world, I already said that, I don't care. But it's very important to understand one of the key mechanisms. Anycasting, the ability to handle this traffic, bring it in locally, is the easiest thing. We can take hundreds and hundreds and hundreds of gigs of traffic and yet spread it out fairly nicely. But here's some things that you can do that really do help you protect your own websites, to protect your own sites, and it's really the key part to talk about, independent of anything else. Running websites that are responding to TCP packets, that are responding to web port 80 or port 443. Make sure they don't respond to other things. Think about your IP layout. Think about how you run sites. Don't run DNS on the same IP as you run your websites. Make sure things are protected as best you possibly can. This filtering is important. So, for example, as you bring packets into your own network, think about the routers, think about the load balancing switches, think about whatever infrastructure, and think about the type of filters that you would add to each item, such that you keep the right type of traffic on the right type of device. For all that attack traffic, whoever is attacked, and of course I'm only talking about attack traffic that came towards us, there's plenty of other attack traffic out there, you have this ability to sit there and say, I don't need to see an email port 25 packet against my port 80 web traffic. I don't need to see a UDP, DNS, or NTP packet hit my TCP-based web server. So again, I use the easiest configuration possible to explain this. So here's a very simple, here's a simple access list. This is as trivial as I can write it. In real life, it is much more complicated, I admit that. But this is the trivialist access list that one could write that shows what we're talking about. If I've got an Ethernet device on a router, and behind that I have some web services, then I would write an access list that permits only TCP, and only to that particular IP address, and only to that particular port, which in this case would be 80 and 443 for regular HTTP web access and secure web access. And then fundamentally the next line is the important one. I would deny everything else, because I don't expect anything else to go there. In real life, life is more complicated for two obvious reasons. One, I should have added the IPv6 addresses to this list. And two, I should also add the appropriate ICMPs just as needed, minimalistically needed. Again, I wanted to keep this as simple as possible to show this is the type of thing. There are lots of examples. Again, I'm using the same website to point to for examples, but that's been a good example of what they've done. The other issue, and I'll sum this up very simply, if you're running an ISP, if you're running a broadband network, if you're running a hosting network, have the good contacts for your suppliers. Understand who you can phone if you have a problem that will help you in dealing with attack traffic in some way. Understand that in as best you can, because it's best to know who to talk to before you have a problem than while you're having a problem. And that really is that's really the sort of the summary of the sort of self-managed ways of doing attacks. We found this at CloudFlare, is that we have the ability to have a hotline into as many of our suppliers as we possibly can to deal with this, predominantly to at least make them feel comfortable that we are also doing something. Attack traffic will affect core, it'll affect all manner of different entities out there, so it becomes a very shared process, part of what I showed earlier within the sort of the whole Twitterverse of seeing stuff happening. On a final note, don't underestimate what the press says. The press love headlines, biggest attack ever. They don't understand what the attack is, but they want to write the story anyway. It's important to make sure the right story is sent out there. We've seen quite a few incorrect articles. I obviously picked the good ones here. Let me finish up. Let me actually talk about. Let me just talk about these core environments that are useful to know about here. This number one issue, I think, maybe my best value of being in front of the microphone. Make sure you're not part of the problem. Go back, look at these websites that can check for Open NTP servers, Open DNS servers, and just make sure that you're not generating traffic unbeknownst to yourself that you don't even know about. The rest of them are all, just run a clean network. BCP38 has been published for an enormous number of years, and it's still taking a long time to get people interested in it. I'm done, and I thank you very much. I can gladly take questions, but I apologize, I didn't have headphones, so I will rely on translation if necessary. Thank you. Oh. Thanks.
Thank you, Martin. Are there any questions? Если есть какие-то вопросы, прошу, пожалуйста, подходите к микрофону. Well, I have a question, but I don't have a microphone.
Oh,
yeah. My question is, to your first bullet on the summary list, don't be part of the problem. It's so easy to mount a DDoS attack, And the people that offer, maybe unwillingly, the infrastructure, I mean, there's 28 million of open resolvers, they don't really feel the pain. So my question, how do you see this kind of dynamics of this arms race? Is it kind of diminishing on one side, or we are getting stronger on another side? This kind of question.
Yes, this is actually a really important question. If you are the creator of this traffic, you may not know. More importantly, it doesn't really sit as an important issue for you to worry about, because it isn't stopping your network from operating. The pain here is felt by the person being attacked. It isn't being felt by the person that's creating it. And this very simple reality means that people are not motivated to fix this. The problem, this has been the same problem for many years. It's very hard to motivate somebody if they are not seeing a negative effect. This background traffic is always there. So there are a collection of different devices that cause this type of problem. We're seeing old broadband routers, some small broadband routers that are open and cause problems. We're also seeing infected laptops, infected computers, of course, and we're seeing occasionally, in this case, the things like open resolvers. But they very rarely go back and attack the broadband server themselves, and therefore they have no cause and effect. It's not only motivation, but the attack is outbound. So the appeal here has to be do the right thing. The appeal is the hardest appeal to do. It is for the good of the internet, for the good of everybody else, that you go back and look internally and see whether there's something you can do. The problem is you may only be a small percentage of the problem, and you've got to convince your competitor to do the same thing, and you've got to convince your random ISP in a random country, and you've got to repeat this and repeat this and repeat this until it makes a big difference. But the only argument that I see that seems to make people make a difference is not so much an argument, but a simple statement. As horribly commercial a statement as this is, we are all here because of the success of the global internet. The growth, the additional mobile users, the additional broadband users, the additional websites that are causing the services that are causing people to go online, and we are all quite successful at allowing this growth to fuel our individual companies. And that's actually okay. We're providing a service, but in order for that to scale, we have to be a little cleaner. We have to look internally and do our own part. This may not convince you to do anything, because it's awfully high level, but it is really the easiest way to state this. Go back, look internally, convince your colleagues, your competitors to do this. Because if we want this internet to continue to grow year after year for the many, many, many years that it should, because we actually don't know what's next. We really don't know. You know, I stand here, but 10 years ago, Twitter and Facebook didn't exist. If I stood here 15 years ago, Google didn't exist. These are sort of, think about what's going to happen in the next 10 years. We don't know. But we need, as infrastructure people, as operators, we need to make sure that we have a network capable of supporting that. And this is some of the things we have to look internally. There is no way for me to penalize somebody. There's no way for anybody to penalize anybody for attack traffic like this. I cannot send you an invoice and say, you sent me 300 gigs of traffic, kindly pay. Because normally paying makes people think. There's no way to do that in this process. And that's life. But looking internally as best as I can pitch and making a difference is what's going to give us the ability to continue growing the internet and, quite frankly, enjoying our jobs day over day. That's the best answer I have.
Great, Steve. Thank you, Martin. And thank you very much.